Einstein once boldly claimed that the laws of thermodynamics were the only physical theory of the universe that will never be overthrown. That all changed late last month when scientists from the Argonne National Laboratory at the University of Chicago found a loophole in the system, one that allows them to break the second law of thermodynamics. The finding has huge implications for our understanding of the universe, not least because it presents us with a chance to one day create perpetual motion machines. These machines, previously just a far-fetched theory, can spin for eternity with no energy input. If hooked up to a power plant turbine, they could feed us with infinite power. The 4 laws of thermodynamics set the physical rules for our universe and were coined by physicists and engineers looking to boost the efficiency of the steam engine in the mid-19th century. The laws determine how temperature, energy, and entropy work together to build and destroy matter. Everything, from the creation of the tiniest atom to the collapse of distant black holes, is controlled by these 4 laws. The researchers found a loophole in the second law of thermodynamics, which deals with transition of energy within a system from usable to unusable. The second law is the reason our phones and laptops need to be charged and that our sun will one day die out. It states that energy cannot repeat in an infinite loop within a closed system, and so we must replenish what is lost. The second law profoundly sets the limits for what is possible in our universe, defining why everything within it must one day decay. Now, physicists at the Argonne National Laboratory have found a small loophole that could allow scientists to bypass the second law, potentially giving us access to machines that generate infinite energy. Some small-scale perpetual motion machines, mostly proofs of concept, have been made and posted to YouTube by amateur engineers and physicists. Underpinning the second law is that entropy, the measurement of quantum chaos driving every particle in our universe, constantly increases. The ANL researchers claim that their loophole could bypass this long-held rule of the universe, allowing the accelerating march of entropy to go in the opposite direction. This would only be on a small, local scale, and for short periods of time. The physicists investigated a statistical concept linked to the second law, known as the H theorem. At the heart of this rule is the concept of entropy, a measurement of chaos between particles. Entropy will always even out in a closed system, so particles in a high entropy area will always flow to a low entropy area until the entropy of each has evened out. Typically, scientists assess the effects of the H theorem by analyzing how large groups of molecules move, as analyzing a single molecule at a time is incredibly complex. But the team at ANL decided to take on the challenge by using a complex set of abstract mathematics known as quantum information theory and applying it to condensed matter physics. The team crafted a new quantum-level H theorem that could read the path of individual molecules instead of large groups. This allowed us to formulate the quantum H theorem as it related to things that could be physically observed, said Dr. Ivan Sadovsky, one of the APL team. It establishes a connection between well-documented quantum physics processes and the theoretical quantum channels that make up quantum information theory. In this new quantum H theorem model, some molecules were seen to temporarily decrease in entropy, shattering the second rule of thermodynamics. The Argonne Lab team has now taken things a step further by brewing up a mathematical model to show how a quantum system could be created where there is a temporary negative entropy gain, in other words, a decrease in entropy. Although the violation is only on the local scale, the implications are far-reaching, said Dr. Valery Vinokur, another member of the APL team. Dr. Vinokur added that the finding eventually could make possible a local quantum perpetual motion machine. Whilst these quantum perpetual motion machines are still purely theoretical, the APL team's findings represent the first big step towards a real, working device.